Welcome, students. Today we're going to look at some complex zeros, and we're actually just going to jump straight into a problem that will demonstrate what we're going to talk about today. So let's find all zeros of the polynomial p of x equals x cubed minus 3x squared plus x minus 3. Now you might be thinking about using synthetic division and trying to figure out what the possible rational factors are and looking at the factors of -3. But unlike most of the previous examples, in this one we can just factor by grouping. If we do that, the first group has x squared as a GCF, leaving us with x minus 3 as leftovers. The second group has 1 as a GCF, also leaving us with x minus 3 as leftovers. And then the two groups have x minus 3 as the common factor and x squared plus 1 as the leftovers. So we have a factored form of our polynomial, and we can set each of these factors equal to 0 to find the roots. The first one gives us x equals 3. The second one is going to be a little bit more complex. We subtract 1 from both sides, giving us x squared equals -1. And if we use the square root property, we take the square root of both sides, and we get plus or minus the square root of -1, which gives us plus or minus I. So the three zeros that we have here are 3, I, and -I. In fact, if we wanted to factor this completely, we could write our polynomial as x minus 3 times x minus I times x plus I, because we know that if a number is a zero of a polynomial, then x minus that number is a factor. So we have found the zeros, and we've also, I believe for the first time, factored a polynomial where factors have imaginary or complex numbers in them. In general, if we ever have a situation where we've got x squared plus a number that's a perfect square, x squared plus a squared, we can factor this into x plus ai times x minus ai. We've never factored the sum of two squares before, and that's because this requires that we work with imaginary or complex numbers. And usually when you learn factoring for the first time, you have not yet learned about imaginary and complex numbers. So this is something that is a little new to us. You're going to get practice with this with the linked video examples below, and you're going to get some practice with problems where we need to do synthetic division and use the rational zeros theorem and do a bunch of other stuff first. But before we get into those examples, I want to talk about two important theorems of algebra. And the first is so important, it's called the fundamental theorem of algebra. The fundamental theorem of algebra states that every polynomial p of x of degree at least 1 with complex coefficients has at least one complex zero. Now, in all of the examples that we've looked at, the coefficients have been real numbers, 1, -3, 1, -3 here. But remember that real numbers are also complex numbers. Complex numbers are any number that can be written in the form a plus bi, where a and b are real numbers. And so a real number, like 4, is a complex number because we can write it 4 plus 0i. So all of the polynomials that we have looked at fit under the fundamental theorem of algebra, and this tells us that all of them has at least one complex zero. Now again, also, the zeros might all be real numbers. That's fine. We just talked about how real numbers are also complex numbers. In fact, this is probably as good a time of any to do a little diagram. So if we look at the real numbers can be split into two types, rational and irrational. And within the rational numbers, that's where the integers go. And then all of these are real numbers. So this is the circle of real numbers. And then this falls inside the set of all complex numbers. So everything that we've worked with, all of the numbers that we've worked with, real numbers, imaginary numbers, integers, rational, irrational, whole numbers, etc., all of these fall under the umbrella category of complex numbers. So the reason it says at least one complex zero is because sometimes we have the same zero repeating over and over and over again. If we looked at the polynomial p of x equals x minus 3 to the 100th power, if you were to multiply this out, you would get a 100th degree polynomial. The first term would be x to the 100th plus a bunch of other terms, lots and lots of other terms. And this has exactly one complex zero. Specifically, the only zero of this polynomial is 3. So we can't really say that every polynomial has multiple complex zeros. This theorem says at least one complex zero. Now there is one more theorem that we're going to look at really quickly, and I'm actually going to write this out by hand because the typing capabilities of this app don't include subscripts very easily, which we need here. So this one is going to be called the complete factorization theorem. Complete factorization theorem. And it says the following. If p of x is a polynomial of degree n greater than or equal to 1, then there exist complex numbers, and they could be real numbers as well. Remember that the set of complex numbers includes all of the real numbers. So there exist complex numbers a, c1, c2, c3, etc., all the way up to cn, with a not equal to 0, such that our polynomial p of x can be written as a times x minus c1 times x minus c2 ... all the way up to x minus cn. So let me underline this because it's a theorem. If we have an nth degree polynomial, we are able to factor it as some complex number times a product of n different factors where each one is x minus some complex number. Effectively, what this is saying is that an nth degree polynomial will have n factors and n zeros so long as we recognize that some numbers may appear to be a zero more than once. In this example that we looked at up here, The 0 that we have is the number 3, and because it occurs 100 times, we say that 3 is a 0 with multiplicity 100. It's just saying that 3 appears as a 0 100 times. You'd never see that or be able to distinguish that on a graph because it's just going to have 3 as an x-intercept. But it's important to recognize that if we have a 0 that has multiplicity more than 1, this doesn't mean we're going to have n x-intercepts. And in fact, if a 0 is a complex number or an imaginary number that's not real, then that's not going to correspond to an intercept. So zeros of a polynomial only correspond to x-intercepts when they are real numbers. If we have any imaginary numbers or complex numbers that aren't real numbers that are zeros, those are not going to give us any more x-intercepts. Now, I know I've said a lot in this video about a whole bunch of things, when in actuality, the thing that we need to get practice with is finding zeros of polynomials that end up being imaginary or complex. So please take a look at the example problems to get some practice with these.